Welcome to part 2 of our lesson on the strip method of slab analysis. We are going to begin by solving exercise 1. In the other part, we read the question. So this is a solution to the exercise 1. We were given a square slab and we were told that the slab is 8 meter by 8 meter. So what we do first is to dimension the slab into edge strip and middle strip. So if we go in this direction, we know from here to here is our edge strip, and our edge strip is A/4. In this case, A is 8, so 8/4 is 2. So that's how we had this place as 2 meters. A middle strip is A/2, which is 8/2 is 4 meters. We have this place as 4. And this other edge strip is A/4, which is 8/4. So we have 2 meters again. And because it is a square slab, in this other direction, we will have the same thing: 2 meter, 4 meter, 2 meter. So that takes care of our dimension of the slab into edge strip and middle strip. The next thing we are going to do is load distribution. You need to distribute the load at every point in the slab. So remember, at these corners, the load distribution is usually Q/2. So please forget I did not write Q/2, but doing this and this means the load is distributed equally into the vertical and the horizontal direction. And you can see here is Q/2, Q/2. The same thing at this corner, the same thing at this corner. But when we come to this space, remember all the load was in the vertical axis and it has a value Q. The same thing here. When we get to this point, all the load was in the horizontal value Q. There was nothing in the vertical. The same thing also happens here. But in this middle portion of the middle strip, the load is distributed equally. Q/2 in the horizontal direction, Q/2 in the vertical direction. So having done that, we have been able to distribute the load to our load distribution. The next thing is, what is the value of this Q? Remember I said that the Q is the load UDL acting on the slab. And so Q is just a usual design load when you are designing a slab, reinforced concrete slab. So we have enough information to calculate that. So we now say we were told the slab is 150 mm. So changing that to meter is 0.15 meter. So the thickness of slab is 0.15 meter. We were given the unit weight of concrete as 25 kilonewton per meter cube. So from that we can calculate the weight of slab. The weight of slab is the thickness multiplied by the unit weight of concrete. That gives us the weight of slab in terms of kilonewton per meter square. Now we were told that the load due to partition and finishing is 1.2, which is part of the dead load. So we can now say that our GK, which is a characteristics permanent action, is the reserve weight of the slab plus load due to partition and finishing. So that gives us 4.95 kilonewton per meter square as our GK. We were also given that our characteristics variable action is 5.0. So we can go ahead and calculate our design load. Design load is Q is 1.35 GK plus 1.5 QK. The 1.35 is actually the factor of safety for permanent action. 1.5 is a factor of safety for variable action. So when we put all this into this equation, we calculated our Q to be 14.18. So our Q is 14.18. So having calculated Q, the next thing is to go ahead and calculate our moment in the edge strip and in the middle strip. So let's start with the edge strip. In this case, because it is a square, the edge strip in the moment in the edge strip in the X direction is the same thing as moment in the X strip in the Y direction. So let's go ahead and see how did we have this diagram. Let's pick the X direction. From here to here, the dimension is 2 meter and the load is Q over 2. That is why we have this 2 meter and the load is UDL Q over 2. You notice that from here to here, there is no load. All the load is in the vertical direction. That is why you have no load between here and here. We also look at here, from here to here, this other edge. The dimension is 2 meter and the load is Q over 2. So we can have Q over 2. So we now have this load distribution. We are cutting a strip of 1 meter width. So this is a load per linear meter. If we first, the next thing we are going to do is that we are going to convert this load. Convert this load into a point load so that we will be able to take moment from the edge, because you are taking moment from this edge. So to take moment from this edge, this Q over 2, if you convert it to a point from a UDL to a point load, you will be Q over 2 multiplied by the length, which is 2 meter. So this is how we have this Q over 2 multiplied by 2 over 1. This whole component, Q over 2 multiplied by 2 over 1. So when we place it here at the middle, remember we are taking moment from this end. So when we place the point load at the middle, it will be at the middle of this load, such that the middle of this load is actually 2 divided by 2. So that is how we have this 2 divided by 2. So when you multiply the whole thing out, 2 will cancel 2, 2 will cancel 2. So we have Q here. And our Q is 14.18. So that means moment at the H strip at the X direction and Y direction is what? 14.18. The next thing to do is to go to middle at the moment at the middle strip. At the middle strip, the end side here, the load is Q. So that's why we have Q here. And the length is 2 meter. So we have 2 meter here. At the middle portion of the middle strip, in this direction, the load is Q over 2. So that's why we have here Q over 2. And Q over 2 is less than Q. That's why this place is less. And the dimension is 4 meter. At the end of the middle strip, we also have Q. That's why we have Q here. And the length is 2 meter. So what we do next is to divide this whole slab into 2. Because if you divide it into 2, half of it will rotate at this end and half of it will rotate at this end. So if we calculate what happens at what end, then we are done. We will be able to get the moment we are looking for. So if we divide this into 2, imagine what we will have. This Q here will still be Q, and this distance will still be 2 meter. So first of all, we change it to a point load. If you multiply this Q by 2, this is how we have this 2Q here. When you multiply it, you're going to place it at the middle of the span of the load. So you by placing it at the middle, and the distance from that middle to this edge is going to be this 2 multiplied by 2. So that's why you have multiplied by 2 over 2. So this bracket takes care of the moment due to this load Q. The next thing is to calculate the moment due to load Q over 2. Remember, when we divide this slab into 2, what will be left in this particular place will be now 2 meter, not 4. So to change to a point load, you will have Q over 2 multiplied by this 2. That is why, and this 2 is the same thing as 4 over 2. So that's why you have Q over 2 multiplied by 4 over 2. That's why you have 2Q. That's why you have Q over 2 multiplied by 4 over 2. So when you now change this load into a concentrated load, you will place it at the middle of that load span, which will be here. Remember, from here to here was 4 over 2. So the middle of it will be what? 4 over 4. So that is how we have, when you place it here, the load will be Q over 2 multiplied by what? 4 over 2. So you have Q over 2 multiplied by 4 over 2. And when you place it here, you'll be looking at the distance. What is the distance between where you're placing the load to where you are taking moment, which is the H? That distance will be from here to here. From here to here will be 4 over 4. So that is why you have this 4 over 4 plus this 2 meter that is already there. You have this 2. So the whole of this component is the distance from where you're placing the load to where you're taking moment. While the whole of this is the point load you have when you multiply this Q over 2 by the span of the load. So if you multiply the whole of this thing out, you will have 5Q. And remember that our Q was 14.18, so you have multiplied, you have 70.9 kilonewton meter. So by so doing, you can see the load at the H strip and the load at the middle strip. And you can see in the slab, the load at the middle strip is far higher than the load at the H strip. So the next thing we are going to do will be to look at rectangular slab. That's what we will do next. So let's continue our lesson by looking at the load distribution for rectangular slab. In the previous one, we looked at load distribution for square slab. So with rectangular slab, it is reasonable to assume that throughout most of the area, the load will be carried in the short direction, and this is in line with elastic analysis. In our design, the short span is usually carrying more load, more reinforcement, which is usually called the main reinforcement, while the long span carries the distribution reinforcement. So because of this, Hillable presented this load distribution. So this is for rectangular slab that has a length of A and a width of B. A is greater than B. So if you look at the dimensioning first, dimensioning in the short span, in the short direction, you can see is similar to the square. You have the H strip is B over 4, where B is the width, the smaller direction. The middle strip is B over 2, and the H strip is B over 4. But in the long direction is A. You see how that the H to be B over 4, this other H B over 4, but the middle part is A minus B over 4. So that is the load, that is the dimensioning for rectangular slab. The next thing is to look at the load distribution. With the load distribution, if you look at the corners, the value of the load is still Q over 2 at the corner, just like for square slab. But when you look at here, at this portion, the value load division is Q. And the same thing here. But you can see at this portion, the next thing you look at this span, this H strip does not pan completely. It's just at the corner, So the whole of this area has a load distribution Q. And that Q is in the short span direction, nothing in the long span direction. That is at the middle strip. So take note of this load distribution because that is what will help us. So if you cut a section like we did in the other one, in the X direction, this is what you will have if you look at it very well, cut section. And in the middle strip in the X direction, this is what you have. In the Y direction, H strip, this is what you have. And in the middle strip in the Y direction, this is what you will have. I think when we solve example, you will understand it more in case you don't understand it here. So that leads us to exercise 2. Exercise 2 says reinforced concrete slab simply supported at all edges is 8 meter by 6 meter and 200 mm thick in thickness. If the total load due to partition and finishes is 1.2 kilonewton per meter square and the total service variable action is 4.5 kilonewton per meter square, analyze the slab and determine the moment at all the critical points, taking unit weight of concrete as 25 kilonewton per meter square. So this is our exercise 2. Again, we are going to solve it. So this is the solution for our exercise 2. That's for a rectangular slab. From the question, we were told that the slab is 8 meter by 6 meter. So the long span was 8 meter, the short span was 6 meter. So first of all, we are going to dimension it into edge strip and middle strip. So if we call this the y-axis and we call this the x-axis, now you need to understand that there is nothing that shows this is just our orientation. This is just our orientation. It doesn't mean that the y-axis must be the short one, x-axis must be the long one. Just our orientation for this slab. So if we come to the edge strip, remember this long short span is 6 meter. So being 6 meter means our edge strip is going to be 6 over 4, which gives us 3 over 2, 3 over 2. We have 3 over 2 and 3 over 2 here. In this our short span, our middle strip will be 6 over 2, which is 3 meter. But this will be A minus 6. It will be A, remember this A minus B over 4. So it's going to be 8 minus 6 over 2. That gives us this 8 minus 3, give us 5 meter. So by that we have dimensions our slab into edge strip and middle strip in both axes. The next thing is a load distribution. As usual, the corner is Q over 2, Q over 2, Q over 2, Q over 2. And in this x direction, the h here is Q. And in this direction, this place, there is not value for Q. Q is 0 and Q here. And in this direction, span direction, Q across the whole span. Please take note of that. So the next thing we are going to do is to determine the value of Q. So the thickness of slab was 200 mm, which is 0.2 meter. The unit weight of concrete is 25 kilonewton per meter cube. And so the weight of slab is going to be this multiplied by this. So we have 5 kilonewton per meter squared as the weight of slab. We were told that the load due to partition and finishing is 1.2. So if you add the 2, you have that one GK equals to what? 5 plus 1.2, which is 6.2 kilonewton per meter square. And so our QK, we were told that the characteristics variable action is 4.5 kilonewton per meter square. And so we can go ahead and calculate our design load. As Q. As Q is equal to 1.35 GK plus 1.5 QK. As usual, 1.35 is a factor of safety for permanent action. 1.5 is a factor of safety for variable action. And so when we put all this into equation, we have that our design load is 15.12 kilonewton per meter square. 15.2 kilonewton per meter square. And by so doing, we have calculated our Q, which is what we will use. The next thing we do is to come and calculate movement in each of the axes. In this rectangular slab, the x and y direction are not the same in both axes. So we are going to calculate axis by axis. So we look at in the y direction, in the x direction. So this is the x direction. Let's look at what will happen. In the x direction, at the edge strip, remember, you are going to have Q over 2 and nothing here, and Q over 2, like we have explained in example 1. And this is 1.5, this is not 15 meter, this is 1.5 meter, this is 5 meter, this is 1.5. So you can come back and look at it, you can see 1.3 over 2 is 1.5, this is 5, and this is 3 over 2 again, which is 1.5. So what we need to do is to change this UDL into point load by multiplying it by the span, which is 2. If you change it into this, you will see have Q over 2 multiplied by 2 over 1. That takes care of that. By the time you place it at the middle of the load and you are taking moment at this edge, the distance from where you place it to this edge is going to be 2, this 2 over 2. So that's why you have 2 over 2. Sorry, I made a mistake to explain this explanation for exercise 1. This is actually for exercise 2 we are doing. Is Q over 2, Q over 2. The difference is this is 1.5, this is 1.5. So again, change this UDL to a point load. It will be Q over 2 multiplied by the span, which is 1.5 or 3 over 2. So that's why you have 3 over 2 multiplied by Q over 2 here. And when you change it, you will place it at the distance of this 1.5 over 2. 1.5, remember, is 3 over 2. That's why you have half of 3 over 2 here. So the whole of this bracket is for the distance between where you place the point load and where you are taking moment. If you do that, you have that the answer is what? 9 over 16 Q. And when you do that, the moment is 8.51 kilonewton meter. That is in the x direction H strip. In the x direction middle strip, let's see what will happen. In the x direction middle strip, from here to here is Q, from here to here nothing, from here to here is Q. So that is why if you go here, from here to here you have Q, from here to here nothing, from here to here Q. So you go back and do the same thing by changing this to a point load. Change it to a point load and it becomes 1.5 times Q, or 3 over 2 times Q, which is this bracket. When you place it, the distance from where you're placing it to where you're taking moment is going to be half of this 1.5, the same thing as half of 3 over 2. You multiply out this, you have 9 over 8 Q. And when you multiply it, considering the value of Q, you have 17.1 kilonewton meter. So the next thing you're going to do is to go into our y direction. This is our y direction. So y direction, let's go to H strip y direction. If you go to y direction X strip, it will be the same as y direction as x direction H strip, because if you look at it, look at this y direction, you see have Q over 2 here, no load here, Q over 2. So it will be the same thing like this. That means our moment my in the y direction will still be 8.5 kilonewton meter. But now the middle strip in the y direction is where things will change. So in this direction at the middle strip, the load acts across the entire span. So you have a load acting across the entire span. So when you come here, that's why you have the Q acting across the entire span. And so what do? Half of this load will rotate at this edge, half will rotate at this edge. So what you need is just to calculate the load at one edge. So if you come to this edge and divide this into 2, so what you will now have, the dimension will be Q acting a span of 3 meters and acting like a cantilever moment. So what do? To change it to a point load, it will now be this Q multiplied by this distance, which will now be 3, or call it 6 over 2. So that's why we have 6 over 2 multiplied by Q. So now what will be the distance? The position of the load. Remember, you have divided this into 2. So what you have here is 6 over 2. By the time you place a point load at the middle of 6 over 2, it will become 6 over 4. So the distance between where you're placing the load and where you're taking the moment will now be 6 over 4. And so when you do that, you multiply. Remember that our Q, when you multiply everything out, you have 68.4 kilonewton meter. That means that you have heavy load, heavy moment at the middle strip of y direction than in every other place. And so with that, we have solved our exercise 2 on a rectangular slab. Thank you very much for listening up to this.